Shall I start?
Sir, I just have to introduce. Yes.
Yes.
Professor Nilesh J. Vasa is a professor, Department of Engineering Design, IIT Madras. Professor Vasa received a Bachelor of Engineering degree in Production Engineering in 1988 from BJTI, Mumbai University, India, and a MTech degree in Mechanical Engineering in 1990 from IIT Madras. He received a Doctorate of Engineering in Electronic Device Engineering from Kyushu University, Japan in 1997. From 1997 to 2005, Professor Vasa was a faculty member at Kyushu University. Since 2006, he has been a faculty member in the Department of Engineering Design at IIT Madras. Professor Vasa has published more than 125 papers in international journals and 250 papers in international conferences. He set up the Optomechatronics Laboratory in the Department of Engineering Design at IIT Madras. Professor Vasa's specific research interests include laser micromanufacturing, laser surface structuring, laser-assisted sensing, optomechatronics, and biophotonics devices. He is a member of Indian Laser Association, Optical Society of India, Japanese Laser Society, OSA, and SPIE. He is an editorial board member of Scientific Reports. Sir is also my co-guide during my PhD studies at IIT Madras. We welcome you, sir, for the talk.
Yeah, thank you very much, Leila. I'm sorry for keeping all of you waiting. Good evening to everyone. And I have divided my talk into two components, two parts. First, I will describe this idea of laser-assisted, right? Yes, 1 minute. No, yes, just 1 minute. Laser-assisted trace gauge pollution measurement techniques. Okay, 1 minute. How to this? I will reduce it. Okay. Sorry. I think something went wrong, correct?
No, sir, screen is there. Sir, are you able to show the shift to next
screen? 1 minute, it is there.
First screen is coming, title slide.
It's coming, no?
Title slide
I went, there. It's coming now, right? It's coming. The second slide
50.
is
second slide
50.
Is.
Okay.
Okay.
So first of all, I'll be discussing about laser-assisted trace gauge pollution measurement techniques. Now, basically, it's very important from the climate applications, environmental applications, environmental sensing and monitoring point of view. And that's why I'm going to describe this work, which has lots of implications, right? Particularly, this gas sensing applications are very much useful in ensuring safety, for example, detection of toxic or flammable gas, etc. But from the environment and climate point of view, we can even use this approach to monitor feedstocks. Okay, feedstocks are related to, let's say, in a bio power plant systems, right, or other thermal systems, etc. And let's say biogas systems, etc., where there are different feedstocks. It can be from the excrement of livestock or food processing company or some garbage, etc. Now coming to the biogas plant, where basically this organic waste, they start decomposing and by a certain bacterial species, and methane fermentation comes into picture, and it generates methane, which can be useful in gas engine, electricity, etc. Now, this methane is also, although it is one of the greenhouse gases, we say, and CO2 is a major greenhouse gas. However, methane has a different its absorption bands are such that it can right, become much more this difficult greenhouse gas, and it has a more devastating effect than even CO2 sometimes, okay, as a greenhouse gas I'm talking about. And so monitoring this methane production, controlling the combustion process in the power plants to measure the biogas quality, etc. Or in case of automotive industry, some of this, right, CO2, carbon monoxide, all those gases when they produce, how to measure such species. Of course, there are various approaches. So as I told you, it can be related to environmental studies, or it can be related to air quality supervision, etc. And recently, there is some interest even in biomedical field to even measure breath and diagnose, right, as a breath diagnostics tools, etc. Now, this type of species which are present in environment or etc. How do we measure such species? Right? Maybe human breath. Let's say those gases exhale are being right. How do we measure this? Is what we are going to discuss right in this presentation, which is going to be the first part, and right how various aspects related to statistical approaches, right, AI-based approaches are also getting into this in order to measure the species distinctively. Now, if we go back to sensing techniques, there are various hardware related approaches. One is a metal oxide semiconductor, which generally is a low cost, right, gives a low cost solution, and but it is sensitive to various other species, and sometimes it is right, sensitive to environmental factors as well, okay, such as temperature, humidity, etc. And it has relatively low sensitivity, but in a high concentration gas environment, this may suffice, right, the application where we know a particular presence of particular gas, etc. However, when we consider right, its use, it has applications, right, because of its low cost, extensively used in civil use industrial applications. But limitations are such that we cannot use this approach for trace gas sensing. What it means, when the concentration, right, is when the concentration is low, right, when the concentration of the species to be measured is very, very low, then because of its low sensitivity, we cannot implement. There are other similar, right, technologies. One is based on the polymer based, which is also useful in terms of right, sensing adsorption of the species, etc., gas species on this, or carbon nanotubes based, which is also based on the adsorption. And when the gas molecules gets adsorbed on the surfaces, the characteristic of this carbon nanotube changes. Maybe it is basically related to maybe the electrical characteristics change or some other physical characteristics change. And we try to measure then the adsorbed gas concentration, okay? However, here also, sometimes many different species, right, may get adsorbed on the same such carbon nanotubes, similar tubes, then difficult to distinguish them. So selectivity, right, sometimes is limited. So selectivity is a question, okay, in this case. Of course, concentration measurements can go up to low level of right, concentrations as compared to the semiconductor-based approaches. But then selectivity, right, is a question. Then there are some other approaches moisture-based absorption measurements, etc., approaches, etc., which are being used. Now coming to the technique which I am going to discuss is optical methods. Why do we use optical methods? Because it's basically non-contact type, right? It allows remote measurements very easily, right? We can measure trace gases or even large concentration gases from distance, right? Then it permits high sensitivity, as I will describe it in subsequently. How is it possible? And selectivity. Selectivity means it can selectively measure CO2 or methane, right? Ammonia, anything, right? Such gases or NOx, etc. Selectively without getting affected by the presence of the interfering gases. Okay, so remote measurements is an important key point, and selectivity is an important key point along with high sensitivity. That's why it is very much useful in air quality measurements. Air quality can be related to environment, or it can be related to a closed environment, open or closed environment. It can be related to power plants, industries, or automotive, exhaust, etc., etc. Okay. It is also possible to use this approach, this technique, for even gas leak detections. Okay. So, for example, methane, natural gas pipelines, methane gas carrying pipelines, etc., when they are going for long distances, right? We can use such optical techniques to measure even and locate the gas leak detection position easily. Okay, so it can be used to locate the leak detection, not only the concentration but even to locate. So spatial such characteristics measurements are also possible. Of course, limiting factor is the cost, right? And that's why maybe it is applicable mainly towards high-end market applications. However, as the environmental aspects, etc., had to be taken care, the technique is becoming useful for various applications. Similarly, there are some laboratory-based measurement techniques. They may not have direct field applications. So there are laboratory-based methods such as calorimetric methods or gas chromatography techniques. Okay, these techniques they're useful for low trace gas concentrations, trace gas concentrations or low concentration species, etc., very easily. However, the difficulty is associated with laboratory applications. So, we cannot use them to a certain extent, of course, on a real-time basis, right? We cannot use them. Immediate response characteristics may be limited. On the other hand, there are acoustic techniques, which are also possible to use. But I will also try to explain, if time permits, that there are photoacoustic approaches. So it is optical based approach coupled with acoustic sound, acoustic generation. So it is known as photoacoustic techniques. And those techniques also have wide applications, right? As they are associated with optical based measurements. So it can allow multiple species measurement, continuous measurement, in situ measurement without disturbing the activity, right? Real time to measurements, and species specific, right? You can monitor different species in the presence of interfering species, and that's why the applications are towards environmental measurements, exhaust, etc. And not only this, as I told you, in power plants, energy systems, where we would like to produce or use these gases, this approaches are useful. For example, in future, when we will be going for hydrogen based fuel cells, etc., or directly hydrogen as the source of energy, when we go for combustion, hydrogen based combustion, etc., we will try to extract this hydrogen from some other species. One of the major potential, I can say, component on this is ammonia, which is potential source of hydrogen is ammonia. Now this ammonia is also very important gas, and it has health hazards, it has environmental aspects, environmental health. It is associated with many aspects related to climate or health, etc. It's although it is a useful source for hydrogen or useful source for various other applications, fertilizers, etc. However, it also has detrimental effect on this, and measuring such ammonia, etc., is an important significant important usefulness. Okay, and wherein we can consider optical methods. As I already indicated, we can use various other approaches, but optical methods plays an important role because it is non-intrusive. As I already mentioned, continuous real-time measurements are possible. Now, how these measurements are possible? It is based on see, whenever any optical light, let's say, it interacts with the matter, some part of the light may get transmitted, some part may get refracted, some part may get scattered, etc. Now, if the light intensity is very large, then it may also produce a plasma, and that plasma may also allow transmission, absorption, etc., various other aspects. Okay, and there may be scattering effect also. All this light interactions I'm talking about. Now, mainly for gas sensing, what type of light interactions we might be interested in? So we generally focus on optical interactions. Sometimes I may be using laser as one of the one of the optical sources. So either some other optical sources or lasers, they interact with gas molecules, and when they interact with the gas molecules, we can observe different effects. One of the effect is these gas molecules may absorb the incoming light source, so there can be absorption. Okay, and there can be scattering. Okay, one of the well-known scattering, when optical narrowband laser source or narrowband light sources interact with the gas molecules, we will see Raman effect, Raman scattering. Okay, so there can be Raman scattering, etc. Now, interestingly, the absorption or Raman scattering, etc., has some signatures, okay, associated with the gas molecules, and and these signatures are responsible. Maybe I'll go to slightly simpler one with the absorption or scattering, etc. So, for example, if we consider a gas molecule, wherein and we'll see the energy, right, states. So let's say y-axis is right, we can say the electronic state energy, okay, and x-axis is basically right, atomic distance, right, in a molecule. So we know that this state energy changes with respect to intermolecular distance. Now, within this intermolecular, interatomic distances, when it changes, within this interatomic, this right distances, when the basically this molecule, this atoms, right, they have a different, right, positions, states, right, this different energy states, and as based on their interatomic distances. Now, because of the thermal aspects, vibrations, etc., which is also associated with the electromagnetic wave, there will be certain such, right, intermolecular vibrations. So indirectly, what's happening? The energy levels, right, are coming into picture at electronic level or vibrational level. When the molecular vibration comes into picture, the energy levels will slightly vary, right, as the vibrations will end up with energy, right, this variation. When the vibrations are at a right, at a level wherein the energy, this levels which are there are very right, this energy difference is much smaller than the electronic state difference, but there is such vibrations and energy level separations which comes into picture, because now when electromagnetic wave, right, incoming optical light or electromagnetic wave interacts with such molecules, the molecules may also absorb some part of the light and may start oscillating with and may jump to different energy levels. So this energy levels, whether vibrational or rotational energy levels, etc., are basically in the near infrared or mid infrared ranges. Okay, what it means that when electromagnetic wave with wavelength around few micrometers interacts with the molecular vibrations, depending upon the molecular structure, atomic, right, this molecular, right, atomic species interactions, this vibrational energy levels may be different. And whenever any particular electromagnetic wave interacts, and if it matches with this energy gap, right, either vibrational interatomic, right, vibrational level or molecular rotational level gap, that particular photon or electromagnetic wave will get absorbed. Of course, the amount of absorption, the strength of this absorption, etc., depends upon various atomic level interactions and molecular structures, etc. However, this absorption comes into picture. Let's say, if I go with, if the optical light source is UV light source, if it interacts with these molecules, there is a good chance that the electron level transition can occur. Okay, while if you are using optical source or electromagnetic source in the near infrared or mid infrared, right, frequency wavelength range, we will end up with vibrational such transitions or rotational transitions, etc., which are responsible for the light, right, absorption. So now when I'm talking about such vibrational rotational transitions, how physically they look like. So if we consider CO2 molecule, it will have vibrations. If electromagnetic wave with a particular wavelength comes, there is if the energy gap of such vibration bands matches with the incoming photon energy of the electromagnetic wave or optical wave, these molecules will start vibrating with the resonance, and the vibrations can be symmetric, anti-symmetric, and symmetric stretches, etc. It can also bend, this oxygen bond, CO bond can bend in different way, as it is shown over here. Maybe symmetric, maybe anti-symmetric, maybe rotational, this is a rotational band, etc. Now all this active vibrations, either interatomic vibrations or rotational vibrations, ends up with absorption of photon energy, and that is the result of basically absorption of certain optical wavelengths when they transmit through such molecules. So just to show you picture really, so vibrations can be of different types. It can be symmetric stretch, it can be asymmetric stretch, or it can be even rocking, rotational, etc. So all these different such vibrations comes into picture, and because of this vibrations, what we observe, various gas species will absorb different parts of the electromagnetic wave. So what is shown over here in this view graph is x-axis is frequency. It can be converted into wavelength, because we know the relationship between electromagnetic frequency and the wavelength. Speed of electromagnetic wave is nothing but the product of a frequency in the wavelength, and we can see that if it is let's say NOx, nitric oxide, NOx molecules, they have certain such absorption bands depending upon which particular optical frequency is interacting with these molecules. Now these absorption bands are coming because of the vibrational, rotational energy states resulting because of the electromagnetic wave interaction with these molecules. Similarly, if we consider methane, it has some different such absorption bands over here. If you consider CO2, for example, CO2 over here, it has such different absorption bands over here. Okay, now these absorption bands are specific to those gas species. Okay, so you can see that of course there can be sometimes overlap of certain such energy bands, but you can see that or from this plot we can easily distinguish, if we want to distinguish CO2 molecule, in the presence of let's say methane, we will see that here methane absorption and CO2 absorption values are slightly different. Here, CO2 absorption is present while methane absorption is less. Over here, let's say if you compare NOx, you can see that here in this region, as compared to methane, NOx has a different absorption value. X-axis is nothing but basically absorption, you can say in terms of absorption intensity, it is not a correct exact word, which it is basically represents absorption cross section, but for for a general understanding, it's nothing but it represents the strength of absorption of electromagnetic wave, so it is quite large depending upon the vibration levels, etc. Okay, this is just for your reference. Water molecules are also particularly water vapor, etc. They have such a wide different absorption bands. And so now coming back to some think part of this spectrum. Okay, only we will not focus on such a wide spectrum. Let's take up wavelength bands. So methane has very small absorption band, but it has, right? CO2 has such different absorption bands over here, right? 1 minute, this CO2 has such absorption bands. This absorption bands comes into picture because of the vibrational transitions, etc. Right, depending upon their molecular structures, different transitions, different absorption bands. And you can see that they are distinct more sometimes, right? Over here, I'm sorry, over here, because this particular things are okay. So methane has bands which is limited to this range, 1620 nanometer, 1640, while CO2 has broadband such absorptions near 1500 to 1600 nanometer, right? Right. So like that, they have different absorption bands. Just to give you an idea, right now, as I told you, when optical light source transmits through the medium, and if the medium has certain molecules, depending upon the light source wavelength or frequency, frequency corresponds to the photon energy, h nu. Depending upon this photon energy, if it matches with any of these vibrationals or translation, right, absorption bands, right, this particular photon will get absorbed while getting transmitted through this, right, molecules. And this absorption depends upon the line strength of absorption. Some of the wavelengths may get absorbed strongly, some of them may get absorbed with the weak absorption lines. Now, this absorptions depends upon coefficient, or the strength of this absorption depends upon sigma, which is known as absorption cross section. And in fact, this absorption cross section of the molecular species into the molecular species density, sigma into n, is known as absorption coefficient. So what is n? N is the density, right, of molecular species of a particular species, what we are looking for. Okay, so molecular species, density of molecular, right, density. So it is a particular species what we are looking for. Okay, so if this laser wavelength is matched with, for example, it is matched with any of this absorption band of CO2. So let's say we have matched it with 1570 nanometer wavelength light. And so when it passes through this medium, we know that if there is methane or let's say CO2 mixture, then we know that it's only CO2 which will absorb this band of light. Okay, so if there are CO2 molecules, they will absorb. Depending upon the wavelength, CO2 has different absorption cross section, and depending upon the concentration of the CO2 present in this, numbers per unit volume or centimeter cube, okay, of molecules will, right, absorb this light, and it is given by absorption coefficient. Okay, so alpha is nothing but absorption coefficient, right, and it is given by centimeter inverse, and sigma is absorption cross section. So now if this electromagnetic wave which is getting absorbed interacts with these molecules, what we will observe is the outcome is in terms of Beer-Lambert's law. Okay, this is the outcome. So if there are CO2 molecules and this wavelength is matching with the absorption, one of the absorption bands of the CO2 molecules, right? So if, for example, if I select absorption wavelength as this, then the absorption is quite low, right? Cross section is low. While I select a particular absorption wavelength, let's say 1570, absorption increases. If I select some other absorption line, absorption may be low, okay, less. So here I will select a particular absorption wavelength, and it has a certain sigma value. And as I already told you, alpha is nothing but sigma into n. Right? Why I'm representing with respect to frequency or wavelength? Because as I told you, this absorption depends upon the particular optical frequency or wavelength, right? As their absorption cross-section values are different for different wavelengths for a particular gas species. So now, if the wavelength is such that only CO2 molecule will absorb this light, and if this light is passing through this gas cell containing CO2 molecule, what will happen? Depending upon the concentration of CO2 molecule, depending upon the wavelength and corresponding absorption cross-section of the molecule, depending upon the path length through which this electromagnetic wave or optical light is passing through this, or gas cell length, Z is known, we can write indirectly. What we are doing is we make use of this Beer-Lemaitre law to determine concentration, because input intensity is known, transmitted intensity is known, path length Z is known, sigma nu for given frequency and molecular species of interest is known to us. Okay, physicists and chemists, they already estimate, right, determine these values, and they have a database. So we know this value. What is unknown is concentration. Okay, that is n is unknown in this, right, measurements. So using this measurements, we can derive concentration, right? And depending upon the path length the light travels through this gas cell, the concentration, right, sensitivity can be enhanced very much, because we know that transmitted intensity is input intensity, whatever it may be, exponent of minus sigma at that particular frequency into n, which is unknown, into length Z. Now, to improve the sensitivity in the measurements, we can simply increase the path length Z automatically, even with a low concentration of this molecules, gas molecules, we will be able to estimate this molecules, as we will see the transmission. There are different configurations to improve this path length, enhance the path length rather, and improve the sensitivity in the measurements. It is also possible to use time of flight, right, approach. So, if we make a cavity with mirrors, so light will keep oscillating. Every oscillation, there is a small absorption. So based on the transmitted light intensity and oscillation, right, the time taken for this light to oscillate, right, if the gas species is present, the time taken for oscillation before it ceases, right, as the output will be very low. So, and if it is no gas species are present, that right, this oscillations will continue for longer time, right, till the light gets scattered out. Now, basically, the sensitivity is the measure of this distance. I have now built in enough inputs in terms of how this right approach can be used for measuring the concentration. So, for example, let's say we consider a gas cell. Gas cell can be a multipass cell, such as like this. So, light can enter. For example, light can enter from here, and from here it goes, light can get transmitted through this fiber and then enter into this gas, right, multipass cell with the right such arrangement, mirror optical right system arrangement, and it can undergo multiple reflections depending upon the mirror configuration which is shown, right, which may be here. So all these reflections will end up with increase in the path length. Okay, and this path length increase will, and if there is a particular gas species present, it will absorb this, let's say, particular electromagnetic wave frequency. So the transmitted intensity will be less. So that's what we observed over here. So we use a laser source, we use a photodetector, and depending upon the input and corresponding transmitted intensity, we will be able to derive what's happening to this light. Maybe the light is getting scattered, or maybe it's getting absorbed, etc. Now, as far as gas molecules are concerned, and not the particulates, etc., the at a longer wavelength, the scattering phenomena may be negligible, it may not change significantly, irrespective of the density of the or concentration of the CO2 molecules which we want to measure. So whatever we measure here as the transmitted intensity is, if there is a difference between input and the transmitted intensity, the losses are mainly attributed to the absorption losses. Okay? Unless this medium has particulates, etc., then scattering will come into picture. Then the losses will be not only absorption, but absorption and scattering together. So now this approach is used to measure the concentration of molecules. Here, please consider, I'm sorry, this should be a capital P. So please consider this partial pressure of gas species present here. We also know from the gas law, or universal gas law, PV equal to nRT. We know that it can be used depending upon the partial pressure of the gas species. We can estimate what is the density of this gas species, so that we can easily estimate. Now, this was a laboratory controlled experiment. We introduce, let's say over here, gas species. Here, what we introduce is C2H2 acetylene in the cells, this system. And when there is no presence of gas species, what you observe is the green color, spectra of the transmitted light. But as soon as some acetylene molecules are introduced in this gas cell, what we will observe, depending upon the absorption band of these molecules, we will see such dips in the output light. Just these dips indicate the absorption of molecules. You may argue that, okay, it need not be absorption by C2H2, it may be scattering of light, or it may be absorption by some other gas molecules. We will distinguish gas molecules at a later stage, but let's say how to distinguish. Is it because of the absorption of the gas molecules, or is it because of the combination of absorption and scattering of the gas incoming light while it is passing through this chamber? If there are any molecules in this gas chamber, automatically, not molecules, I'm sorry, particulates, much larger in size as compared to this molecules, the light will start scattering here and there. So the transmitted signal will decrease. However, what has been found that if the wavelength of two light sources over here, let's say we consider 1550 nanometer, this is the light intensity, and here we consider 1520. Now, for corresponding to the input spectra of the light and corresponding to the wavelength, okay, if the wavelengths are nearby, a few nanometers difference or few tens of nanometer difference, what will happen, what is expected, that the scattering coefficient, so when we consider scattering, this scattering coefficient is almost the same between two absorption lines which are nearby. Okay, and so the advantage is, if I use a slightly broadband source, then we will be able to simultaneously measure the presence of scattering and molecular absorption. Okay, so this approach can be used to determine different gas species. For example, here there is a mixture in this gas cylinder system where this particular absorption cell contains some gases, okay, which are coming from different parts, right? It may be, if it is an industrial exhaust, it may be gathered over here, small amount. And then the light passes through this, and to improve the path length, what is done over here, we have used corner cube prism, and transmitted light again passes through this, and detector detects this. Now when it is passing through this gas cell, light passing through, if the absorption band of the absorption band of the CO2 molecule and the electromagnetic wave which passes through this matches, we will see such absorption, etc. And these absorptions are because of so in the absence of these molecules, what we will see is a spectrum such as like this. Okay. As soon as molecular absorption comes, there will be some absorption lines. And based on the transmitted input intensity, transmitted intensity at different wavelengths, we will be able to derive the concentration of gas species. Now, to explain you further, that if I select different wavelengths of the light and different 2 micrometer, 1.8 micrometer, 1.39, etc. What we can see that if I'm selecting a 2 micrometer wavelength light, CO2 molecule, will have absorption. Of course, water molecule will also end up with absorption. So there is an interfering, thing. To distinguish this, water, vapor and its concentration, we can select another absorption line by water, okay, molecules. Let's say, for example, we will select 2.6 or 7 micrometer or 2500 to 2700 nanometer light. It will get absorbed by water molecules, but it will not get affected by the absorption will not be present with CO2, and maybe CO, there is a species, we can select slightly different wavelengths such that the absorption interference can be avoided, and we can measure different gas species and their presence using the Beer-Lambert's law, which I described in the previous case. Now, this I will skip for time being to make it simplified. We can use this approach, what I explained to you, for point sensing technique, point sensing. Wherever we assign the particular wavelength light, and if there are any gas molecules which absorbs this incoming light source, because of its resonance coming into picture, then the transmitted light intensity will decrease compared to the input, incoming light intensity. And using Beer-Lambert's law, we can estimate what is the concentration. If there are a mixture of species, if there are two species which are mixed together, we may need two wavelengths to distinguish them. And if there are three species, we may need three wavelengths, optical light, to distinguish them wherever specifically, either eliminating such absorption band, or by using a matrix method, and with a statistical approach, we can easily distinguish. Now, there is one more aspect associated with this gas species, etc., and that is remote measurements. What we considered is a point-to-point measurement. So in case of remote measurements, the technique which is used okay, is known as LiDAR, light detection and ranging, and we can make use of multiple wavelengths and overcome the difficulty which is being used to measure methane and water vapor, etc., at a higher altitude. Okay, so this is basically weather balloon payload. Okay, and it is being used. So now, as I explained, I can make use of, instead of using such weather balloon payloads, putting measuring instruments in this and measuring the concentration, what we can do is we can shine the atmosphere with the light, an electromagnetic wave of, means basically electromagnetic wave of a particular wavelength, and see the reflected signal. This reflection comes into picture because of the scattering. And scattering comes into picture, right? Because of some particles, because of some other molecule species, etc. Right? So to distinguish that, we can change, as we already learned, that we can change frequency or the wavelength of the light source and see the reflected light source and its intensity. Now, this intensity results in absorption, right? If it matches with the absorption band, it is being absorbed by the. So I can now measure remote measurements over and above. Now I can also find out from where, at what location this absorption is coming into picture. Okay, so see, when light is getting transmitted, it's getting reflected at various points because of the particulate scattering, etc. Now, scattering of the light will have a different time of light from different distances, right? Time of light from this position will be different than the time of light from this distance. Hence, there will be positional location, which we can find out based on the reflection from where it is coming, and absorption will end up with the intensity change. So how will this look like? So absorbing light wavelength passes through the atmosphere, and non-absorbing light wavelength passes through the atmosphere. Both wavelengths are very nearby, okay, but one is getting absorbed by the gas molecules, the other one is not. And when there is a reflection coming into, when the reflected is because of the scattering, because of the particulate scattering, etc., particulate matter, the light is reflected back, right? Then you will see that this particular band, right, absorption band, is intensity is reduced because of the absorption by the gas species present in this cloud or in this region, right? And the reflected light coming back with wavelength which is not matching with the absorption, you will see that the intensity is not reducing. Now, if I plot x-axis as the range or the position from where the light is reflected back, right? And the y-axis is the reflected light intensity. What we will observe, if there is no absorption till this position, okay, there is no absorption, then the reflected light from the absorbing light or these two different light wavelengths will be overlapping, right? As soon as absorption comes into picture, the one of the light beam, which is lambda on over here, matches with the absorption band, the intensity starts reducing. As it propagates through this medium or a cloud, the absorption keeps coming into picture because of the molecules present over here is absorbing this incoming light. So depending upon concentration, depending upon the path length, the absorption, right, will decrease like this. While the light which is not going to interact with the molecules present over here, or it is not absorbed by this molecule, will get reflected back, right, without any such right, changes in the light intensity. Okay, so this absorption or decrease in the light intensity and position from where the changes is indirectly gives us the concentration of the trace gas molecules which are present, and the second location where they are present. Okay, so we make use of this type of approaches to measure even the concentrations of the trace molecules at a remote distance, maybe few tens of kilometers away or even longer length, till the light passes through the cell. So this is one approach of using a light source passing through the telescope to the for a long distance. The reflected light source is being collected by the telescope onto the detector, and the sensor over here detects the reflected light intensity with respect to the time as shown over here, and measures both wavelengths in one wavelength which is matching with the absorption band, which is lambda on, another wavelength of the light which is not matching with the absorption band of the molecular species of interest, lambda off. And we can make use of mathematical analysis to estimate this absorption based on the Beer-Lambert's law and the reflections from different places, from this cloud position, from this cloud position, from different molecules. All these aspects are can be captured with this, and we can measure the concentration of the species present. Like this, this approach has been used to measure ozone, water vapor, in troposphere, stratosphere. We can use measure SO2, chlorine, nitrous, and nitric oxide, or NO2, nitrous, we can say nitric oxide. If it is N2, nitrous oxide, etc., we can measure. Mercury also can be measured. So there are various ways to measure this, and the same technique is extended. Absorption-based technique has been extended to measure various molecules such as CO2, methane gas, etc., etc. Okay, so this is the it can be useful to measure concentrations of CO2 present during daytime, in the during daylight, or in the night time. We can measure various such at time levels, even along the road which is congested traffic, or in the forest, etc. How this molecular is methane or CO2 or water vapor changes with time. All this parameter can be captured using this LiDAR technique, with the absorption light sources, with absorption bands matching with the light wavelengths matching with the absorption bands of the molecular species of interest. And with time, we can measure the transmission. We can even measure, such measurements are possible by using the light source, So this is a LiDAR scanner. So in airborne system measurements, we use the light source in the on the aeroplane, and or on a aero vehicle, aerospace vehicle, or aero vehicle, and what light passes through the atmosphere. Reflected signals are used to measure the concentration of the trace gases, position of the presence of the trace gas, where is it present, etc. We can easily estimate. Now, in the space-borne LiDAR, we can make use of satellite systems, or even a space shuttle, to measure the trace gases. And by using the satellite systems, we can even find out position from where we are measuring this, species, etc. So it is possible to measure either from line, right? So we can use a mobile system, or right, lane based, right, LiDAR systems, wherein the laser source or light sources are on right, earth, right, located on the right of lane, and lasers are used to find out this trace gas concentration, or it can be airborne, or it can be spaceborne. We can measure, right, such concentrations for right, plot various such species, presence of species. We can measure mixture of such gases, mixture of gases using different wavelengths, one matching with methane gas absorption, another wavelength matching with CO2 gas absorption, another wavelength matching with NOx, or right, NO, nitrous oxide, nitric oxide, etc. One matching with H2O vapor, one matching with ammonia. So we can measure various gases. It can be mixture of gases, right? We can even use some of the trace gases may have absorption lines matching with each other at such different wavelengths. In that case, we can use statistical approach, matrix method to right, distinguish right, different species, measure the concentration of species, etc. So we could right, we can see that it can be right, ground based LiDAR, it can be airborne based LiDAR, it can be space based LiDAR, it can be right, a sea based LiDAR. We can use to measure concentration of various species, right, without any difficulty. Of course, there are challenges how to make this approaches compact and measure the combustion, etc. Various, how the automotive exhaust, combustion engine exhaust, etc. works, etc. There are challenges. We can also use, there are challenges in how to measure hydrogen gas, because the absorption wavelengths of hydrogen gas molecules are in the vacuum ultraviolet region, VUV region. They don't have absorption bands in the longer wavelength regions, etc., like such as in mid-infrared, etc. They don't have absorption bands. What type of approach should we use? Although today I didn't discuss, but here same this transition lines, right? Vibrational transition lines will take part as I described in the beginning, but associated with Raman scattering. Okay, so we can use Raman scattering technique and use this vibrational bands associated with the light of molecular structures, and then estimate the right hydrogen molecular presence, etc., or concentrations by modified approaches. So that is possible using this. So this part, although I took little more time for explaining this part, is completed. Before this, I also would like to explain you something slightly different, slightly interesting aspects related to 1 minute. 1 minute. I'll just come out, and I will now present this part. Okay. A little bit, I'll quickly go through. I'll not take much time, 5 to 6 more minutes, to give you an idea that it's not only absorption based measurement. Okay, in the previous case, sorry, I'll have to make it. It's in the previous case, in the previous presentation, I discussed about mainly associated with absorption, right? Optical absorption and associated specific absorptions corresponding to molecular presence, etc. Now, over here in this, I'll be quickly describing you that we can even use laser-induced, right, breakdown spectroscopic approach for analyzing some of the elements present. Okay, solid elements. It can be even liquid. It can be solid, right, liquid, or it can go up to even gaseous species, right? But generally, solid is very easy to analyze using this tool and estimate the elemental presence here. Okay, so how it can be useful for energy, environment, etc. is right. We can use this to analyze coal samples. We can use to analyze presence of ash in the coal samples, etc., using this LIPS tool as right universal tool to analyze the coal, find out the ash, or in coal find out the presence of carbon or other atomic species, right, etc. We can see. Right, so this technique was first right introduced in Los Alamos laboratory for analyzing some of the nuclear power plant related species, etc. But let's come back to our basic understanding of this, how this technique is used. Quickly, when the laser with a high intensity laser pulse interacts with the material will absorb part of this incoming high intense laser pulse, and it gets thermal aspects comes into picture, and it gets vaporized, right? And this part, if the intensity is small enough, we may go up to heating the target, or we may go up to melting. But if the intensity is large enough, we may end up with vaporization. And sometimes thermoionic emissions in this vapor, electrons, etc., will absorb the incoming light, and this vapor gets converted into hot plasma, because the incoming light will be absorbed by the electrons, free electron, etc., thermionic, because of the thermionic emissions within this vapor, and this electrons starts absorbing this light, and then plasma formation comes, ionic species, etc. And right, this plasma formation right expands very fast. Now, in the absence, once this laser incoming pulse ceases, then this expanding plasma cools down. Okay, it cools down, and when it is cooling down, some of this species, atomic species, which got ablated from this because of the laser interaction with the solid matter, and that the matter got converted into vapor, then plasma got ablated, right? That atoms which got ablated, they cool down in this plasma which is cooling down, will bring back this right atoms to the ground level, the energy states, and then there will be some optical emissions because of this transitions of atom coming back to their ground level. So when laser interacts, lots of such atoms and ions are produced, and this atoms, ions, where electrons might have jumped to the higher energy levels because of this laser matter interaction. And when there is no laser, this atomic species or ionic species, when they cool down, they will electrons from upper states, excited states, will come down to different energy levels. Right? One more minute. I'm sorry. And then you can see the characteristic emissions, which will look like this. So in the excuse me.
That's some participant maybe. No problem, sir.
So when laser interacts with the matter, it will emit various species, such as like this. These species are because of the atomic this ablations and then plasma cooling down, right? And this species are this emissions, because of this emissions from the species are captured in using spectrometer, and that indicates the presence of this molecules. Now this technique can be used by using a laser pulse ablating the material, observing this cooling plasma and atomic line characteristic emissions from this atomic species, and observing the spectra. Generally, we use a nanosecond pulsed laser and to ablate the material with a very high intensity, and then use a spectrometer to detect various optical emissions from this species. Okay, so and then that species can be used to determine. So I will just go to, right, it has been used in Chandrayaan, in Mars, etc., land rovers, etc., being used to detect the element presence on the things, of course, but I'm skipping those, right, aspects. What I will show you that this ideas can be used so because of the time limit, I'm going little tweaking, right? So we can use to measure the coal composition. Okay, the presence of carbon in coal can be estimated by using such approaches. So when laser ablates the coal, there will be lots of different molecular and atomic emissions coming into picture, and in the presence of the atoms and molecular bonds, etc. And those optical emissions, right, are used to detect the presence of such atoms or molecules, etc. In this. And if the carbon is present, we will see some strong bonds such as carbon 1 species presence, or carbon nitrogen CN bonds, or right C2 bonds are observed in terms of optical emissions. And the intensity, from the intensity of the optical emissions and other parameters, we will be able to even estimate the concentrations of this. Even the particulates, coal particles are present, that also can be captured. We can capture the optical emissions from those coal, pulverized coal particles, and measure the presence of carbon, carbon or other species such as aluminium, silicon, calcium, etc. Okay, so this approach is being used to measure the concentration of the gas species in coal species over here. We can instead of coal, it can be some other solid material that can also be analyzed. But this is basically the coal species that I wanted to explain, because it is associated with the energy, right? Thermal power plants, etc. So it is associated with the energy, and that's why I described this. So thank you very much for listening to my presentation. Although it is not directly connected with the various technologies, right, artificial intelligence, etc. But then these approaches are being used and being extended in order to combine with artificial intelligence to improvise the detection limits, to improvise the accuracy of the measurements, to improvise or to reduce the interference of other species, right, elemental species presence and interfering the measurements, that can be avoided by combining the laser based absorption techniques or laser based breakdown spectroscopic techniques with artificial intelligence, or right, some other matrix approaches to distinguish and selectively identify certain right species of interest. So once again, thank you very much for your presence, online presence. And if you have any query or etc., please welcome.
There already one question in chat box. What is the effect of frequency for LIPS analysis?
Okay, so the frequency wavelength, laser wavelength, has not very important role as such to play in LIPS analysis, other than it should be effectively absorbed, right? Efficiently absorbed by. So if we are using laser wavelengths of the order of 1064 nanometer wavelength, or even 532 nanometer or 355 nanometer, they all will be useful for ablation, etc. However, sometimes some of the optical emissions from the elemental species, right, may be this incoming laser pulse should not interfere with such optical emissions. Otherwise, our spectrometer, our detector, etc., will not be able to then distinguish, right, between the laser pulse, which has a very, very, very high intensity, right? Even if the scattered light after the laser pulse is over, that scattered light itself will interfere with the optical emissions of the species, right? So if the wavelengths are not matching, laser wavelength and the optical emission from the species, if they are not really overlapping, not much of difficulty. And compactness, if I want to use a compact source, I may use, right, some compact sources, then I may use diode pumped NdArc lasers, etc. So generally 1064 nanometer wavelength or 355 nanometer wavelength of the NdArc laser, they are being used for such analysis purpose. We can use longer wavelength, but then the effectiveness in terms of absorption, right, by the material will play the role, and sometimes compact laser sources may not be available, right? We can use shorter wavelength, extremely short wavelength, but then if we are using shorter wavelength, the laser source, right, compact laser source may not be available. So these are the aspects that we consider while LIBS process is taken, right?
And Seema Srivastava is asking to enlighten more on carbon nanotubes application.
Okay. So although I didn't go into details, right? Why do we use such carbon nanotubes or structures, etc., in absorption measurements, etc.? Is basically the carbon nanotubes, because of its own structure, right, allows large surface area, right? Large surface area means the gas species, right, all which are coming in contact with this such carbon nanotubes, the absorption by carbon nanotubes enhance, right? The gas species will get absorbed because of the large surface area of the carbon nanotube on the carbon nanotube materials. Now, with the absorption of coming into picture, the characteristic of the carbon nanotube, the characteristic of that device in terms of resistance characteristics, etc., changes. Okay, because of the gas molecules which are interacting with this carbon nanotubes, etc., some reduction process, etc., comes into picture, and because of that, the electrical characteristics of such tubes changes. Okay, and we measure the change in the electrical characteristics, which is in turn associated with the absorption of the gas species on the, right, or indirectly concentration of the gas species present in surrounding, etc. That's why carbon nanotubes plays an important role just to enhance the surface absorption and make use of the electrical characteristics subsequently to measure such
But sir, as
changes.
per my knowledge, carbon nanotube manufacturing is not that much
Easy.
easy and not developed yet, isn't it? Because
Yeah, that's why.
but practically, whatever you're saying, it is practically implemented or just a simulation work?
No. Carbon nanotubes, there are, see, we are not using in optical measurements, it is not essential to use, right? It's only optical light which interacts with the molecules and absorption comes into picture, isn't it? That is clear to you, I hope, right? At least something. Now,
Yes,
coming to the approaches where we do not use optical methods, but we use semiconductor-based devices or carbon nanotube-based such as devices, where we allow gas species to get adsorbed on the surface of this. So they are all point sensors. Their sizes are not large. They are few millimeter size, few centimeter size. They act as a point sensor to detect the presence or concentration of the species. And they are very much used in applications. They're very much used, okay? Of course, the application of carbon nanotube may be limited due to other reasons in terms of its manufacturing, right? In terms of other technology to be developed for depositing it appropriately, etc. So that technology is being developed. So the usefulness and right is increasing. However, they cannot compete with optical techniques whenever remote measurements are essential, whenever wide area measurement is essential, whenever very high sensitivity is required for measurement, whenever different species to be distinguished, right? Because even methane may get adsorbed and some other species, water vapor may also get adsorbed on this semiconductor material. They may interfere in the right measurements, right? Water vapor may also have some negative influence on change in the resistance. Methane may also have some other influence. Then I will not be able to distinguish between water vapor concentration and methane concentration. In that case, optical techniques can easily distinguish because we use specific wavelength for specific species to be determined.
Sir, sorry, one more question. Sorry, ma'am, can I ask?
Yeah, sure. Yes.
Yeah. Sir, many times in landfill, no, fire catches because of huge methane emission there. So can we use such thing there so that the fire will not be catch at the landfill sites?
So now I do not know why in landfill, right, methane comes. But you can, I can give you another example, maybe relevant in coal mines, for example, okay? There is, of course, we are extracting coal in the coal mines, but there will be many gas species which are present. And sometimes even high pressure gases are also present, right? Because they are also a byproduct of such various processes happening over so many thousands of years, right? And carbon monoxide, carbon dioxide, methane, other organic compounds may be present. Not only coal, not only oil, but gaseous species are also present. Now, when we are doing coal mining, there may be a presence of such species, and they may end up with a blast, right? Because of some electrical sort, because of some other, right, cause, electrical energy, or because of that, and we end up with a blast, and that or poisonous gases, which may end up in poisoning, right, the atmosphere. So, how to determine the presence of such gases, either trace gases such as poisonous gases, or trace gases which may be methane, etc., which are highly volatile organic compounds if they are present. How to determine? For such applications, this technique, optical techniques, are being explored, are being developed for such measurements as well. In that case, you may say, how will I transmit the light? Right? I can transmit in a free space, or even in a mine. If it is a long enough, I can even transmit the light. Or sometimes we simply bring in optical fiber based measurements, right? We bring the light from the outside lane, right, ground, bring the light into the mine, and the reflected light will transmit back outside, so that measurements will be done safely and we can measure the ambience, right? Presence of trace gases, etc. within that space, right? Earmarked space or in area, and it can be used. So even along a gas pipelines, not our household gas pipelines, I'm talking about the gases being right transported along the gas pipelines in right various places where these gases right are being natural gases are being extracted, right? So how are they used? They are being then transported via gas pipelines. So sometimes, right, or many a times, then to measure the leakage in the gases along the gas pipeline, etc., we can use optical techniques to measure such gas species. Am I clear, ma'am?
Thank you, sir. Thank you so much, sir. Yes.
Sir, one question on whether the LIPS is available in IIT Madras SAIF testing facility, SAIF, SAI, SAIF, sir.
SAIF, it is not there because generally we use it in laboratory, we ourselves develop. So in fact, Dela had also developed such a technique for biofouling measurements, right, on marine structures, right, etc. So she had developed that technique. So then it is we develop it's not, I cannot say that we develop the laser, we buy the laser, right? We go towards applications. So we integrate optical systems with the laser, spectrometers, lasers, other optical systems for laser ablation and measurements. So we have in our lab such systems, but we need calibration. See, I didn't talk today due to the time. Maybe I took more time in explaining you some fundamental approaches, etc. So I'm sorry, but it is not very easy when we use LIPS because we should calibrate with the standards and then find out, right, how effective are they in measurements, etc. So, but it is possible, right? It has been used for various measurements, and if there is some interest, right, we can also try it out. Such
Yeah, this was asked by Dr. Venkitesh, sir. Dr. Venkitesh.
Yeah.
Sir, one more question in chat box. Sheikh Zakir Hussain is asking, is the mobility nature of gas molecules considered in absorption?
See, generally, optical techniques and the measurements are very fast, right? They're very fast, right? So by the time we measure we do not expect the optical molecules to go very far, right? Very away mobility, etc. So it doesn't affect much in terms of overall measurements, right? As such directly. But if we are trying to measure based on scattering, etc., we may be able to even estimate the mobility. In fact, using laser, you can even measure the mobility of such gas molecules to a certain extent, right, etc., by Doppler effect, etc. But keeping it aside, such aspects, right, if we want to measure the concentrations, I do not think that the mobility will play a major significant role. Okay, may not be playing a significant role in terms of error during absorption measurements, etc. Okay, but we can measure if the gas is getting mobilized, we can measure how it is spreading with time, which we can use laser at different point of time and see how the gas species are getting, right, mobilized. That we can see, right? We can find out such traces, etc. So there are research groups, they work on measuring such, right, the path along which, let's say, for example, how ammonia is leaking or how methane gas is leaking, how it is getting sprayed, etc. We can measure all such patterns, etc.
So that much are the questions. If anybody wants to ask, they can ask directly also.
You're welcome.
Yeah, I think, sir, it's sir, I think no more questions in chat box. Yes, sir. So thank you very much for the session, sir. Yeah, it was very in-depth.
Thank you.
So you took a lot of pain, like using.
No. I'm so
10.
sorry. I went to little bit more of basics so that once they understand, they will be able to, anyone will be able to extend that approach. And right, I hope the things, some of couple of few slides I have used what Dela has prepared. I hope that Dela had prepared well. Right, she was doing.
I think because it exceeded, many participants have left. Thank you very much, sir.
Thank you very much.
Thank you, sir. Thank you, sir.
So sorry for the
No problem, sir.
exceeding
No
the
problem.
time.
Thank you very much, sir.
Thank you. Bye.
Bye. Bye. Yes, sir.
And
Participants' feedback link is shared.
yeah, and
Yeah.